Welcome all to the EasyPower Tuesday Refresher. Good morning. You are welcome to contribute to the discussion by submitting questions or comments during the session. Today, in the time allotted, we will attempt to overview the most frequent mistakes encountered in an arc flash study. And while several really can be categorized as beginner errors, many others are actually committed by individuals with significant experience. We usually try to start each session with a poll question, and here's where we're going to go today. So if you would please contribute and participate with some feedback, and it'll help steer the conversation. Very much appreciate you attending and your contribution to the session. Leave this open for about another 5 seconds. Thank you. So here's how it looks. And then the next question is, what part of the sessions or the study is most problematic for you? And this will vary. Sometimes even more insight with people that are more experienced, having an understanding of where they have more issues. Give this another 5 seconds. Thank you. Here's how the results there looked. And then finally, how long have you been using EasyPower and how that kind of pertains to the conversation. Give this another 5 seconds. Thank you. Here's how the results there looked. So now, as I indicated, the first mistake, if you will, the first error that we see very frequently is what I consider to be a beginner mistake, but it's due, in fact, to trying to be too quick to complete the task. And an advice that I offer everyone, especially when you're not starting a new study, is to start small and verify the methodology you're using, the mechanics you're using, and the purpose of the study are being met, and that you understand how that process is taking place. I recommend it even before you start the data collection, because by understanding the parameters as you start, you have a better chance of not having to go back and do a second round or a third round of data collection as you realize maybe your first attempt at it wasn't that satisfactory because you didn't have adequate data. And then what happens if you already built a one-line diagram and you're starting to have problems without having to go through this verification, and you can get trapped into what I consider a rabbit hole where you fix one problem and you uncover 3 others. So I want to jump into EasyPower and show how that works. So frequently we'll receive a one-line diagram that looks like this, and the problem with that is when you go to short circuit focus, the tool says, well, you've got some data missing, and you're given a long list, a laundry list that identifies virtually everything that hasn't been completed, or in some cases even connected correctly. And so if you start with that approach and you start fixing all these problems need to be fixed sooner or later, but if that's the way you're going to go, it's going to take a long time before you even get any kind of appreciation or progress for what you're doing. What I've done, what I recommend is, if you can, start small and do some small representation that takes a continuous link from the utility to one of the loads, probably the farthest load from, and as far as the hierarchy of the system, to make sure that what you're trying to do is satisfactory. Now, in this particular case, we've already got a large one-line drawn. What I've done is gone through and deactivated a fair amount of it, and by doing that, we can eliminate or narrow down the places we have to deal with. And you can see here I've deactivated most of the one line, and what I'm going to be looking at is this left-hand block over here where I still have some errors. Now though, I can go through, look at my error list, and I want to take a real quick screenshot of it as I work on this list to fix it. And now this allows me to get to the point where I'm actually seeing whether or not what I'm trying to accomplish is going to give me the results. So I'm not as concerned about the accuracy of the data as much as I am the accuracy of my mechanics. So to fix these particular problems, I'm going to copy and paste the adjacent cables, because that's obviously causing an error. If I go back and look at I've got another cable in the utility. The tool lets me find the specific devices fairly quickly. I can go to the utility again, and you'll see this. You actually uncover several mistakes. It's going to be on my list as we go into this. You can see I have a problem here with my utility. I'm just going to deactivate this, put in another standard utility icon, and use that instead. And then I think my last error is this down here, so we're going to find out what's missing. And again, if I don't have this data or I haven't entered it properly, it doesn't get me as far as what I'm trying to accomplish. What I'm trying to accomplish is to verify that my system works. So as I go into short circuit my system, the mechanics of what I'm trying to accomplish. As I go into my short circuit focus, now what I can see, and the tool will only present to me the buses that I have activated, and as I go back to the block that I was trying to verify that I have valid data on, which was through the ATS over here, I can see that I'm getting results, albeit high energy levels. I'm seeing connected results and continuity through transformers, and the point is now I can actually go through the rest of my list and verify that my methodology is correct. So the encouragement, frankly, is to not be in such a hurry to start large and take a more measured approach, understand what's happening before we start building a large one-line diagram. So let's go to the next one. We're going to see, you actually can see that many of the examples that I bring up, they'll have multiple problems with them. So let's kind of go to the next one. Okay, again, improper system modeling, we're going to find, and easily at least once a week, we'll have files come in, and the biggest result is that there's no valid device found. What I recommend is you start at the utility, put in what you know to be a valid data entry for a single device, and then go back and find out, one, is your connections proper to the level you want to go to, and then go back and start the error correction on the rest of the system. So here's how this works. I want to find my example folder. All right, so again, we're going to go in and short circuit focus, fault the buses. Nothing shows up on my one-line diagram. The next step always should be to utilize the arrange for arc flash analysis icon, and instantly I'm seeing that I have no valid device found upstream, and yet I've got tons of breakers and whatnot in there. So like, what the devil's going on? Well, what I suggest is you go to your database editor. Let's put in at my utility a typical cutout fuse. In this case, I'm going to, because I'm at 1247, I'm going to use an AB chance fuse that I use all the time. Put a fuse into my cutout switch, characterize it so that I know it's going to be recognized in the system, and that means enter the manufacturer's part number, the type, and my go-to is AB Chance Fuse Link Model T, because it actually was part of a conversation I had some time back with a new user. If I've entered the correct part number, I click Calculate. The tool says, okay, I find that device in my library. Manufacturer tested it with an X over R of 15. Now I can go to Short Circuit Focus, fault the bus. All of a sudden now I have numbers all over the place, and even better, I have results through the majority of my my system. Now, what that tells me is every one of these devices is improperly set up, because as I look at my upstream device, the only device that's being referenced is the fuse that I put in. So at this point, we see that there's something being calculated. Interestingly to note is that one of the requirements of an IEEE application of the model is to compare 85% with 100% arcing current, and the tool, when we're showing magenta type on the arc flash hazard spreadsheet, indicates the 85% value of the arcing current is being used, and that is somewhat characteristic of fuses because of the slope of the TCC curve. All right, so again, what we're trying to do is verify that we have connections and we don't go off and change a bunch of things until we know that the fault is general in terms of how we've entered data. Now, as we go, we'll get into details on this as we get into more specifics, but just picking one of these breakers out, as I look at the way the data was entered, I entered a part number, but that in this case stopped. I don't have breaker type, breaker style, or short circuit information, and the tool gives me a clue when I start to be more careful about the information I'm requesting. In terms of elements, for an arc flash study, generally you need to detail the first 3 or 4 tabs in every device, and the more complicated the device, like a tripping unit or a relay, the greater number of these tabs need to be filled in. Easily once a week, we see that particular problem. Next most common mistake, and this actually has come up just in the last couple weeks, and that is, if I'm primarily looking at a 208 volt system, should I expect to see a high energy level? And this kind of is not necessarily a straightforward discussion in IEEE and NFPA annals, but it's a place where I think you apply a fair amount of common sense, and if you've gone through the process of trying to understand what the tool's telling us, there's a lot of value in taking a jaundiced look at what we see when we see a 208 volt system that's showing us 240 calories on the label. IEEE says less than 240 kVA as my power supply, in a system that's 240 volts or less, supplied by 125 kVA or less, can be disregarded because it's a low risk of arc flash explosions. The issue there is the 1584 model is conservative in that it gives high values for those numbers, and that's why some cases people stop when they see elevated energy, do the calculation, thinking it's all the fault of the model. Well, in more recent designs, in older systems, it is possible to have energies that exceed nominal levels in these low voltage systems, but in more recent designs where we have distributed protective devices, there's really no way we can get that high of an energy level. So let me go out and find this example and let's talk about it. Now in this particular case, I've actually just drawn a subsystem of the one line that was sent in and replaced the upstream transformer and some of the higher level distribution systems with the representative bus that's showing our available short circuit current and the X over R at the bus that we're coming to the ATS on. And as we go into short circuit and fault the buses, indeed we do see we have an elevated incident energy. So the first thing I want to look at are my short circuit options, in which case the ARC flash hazard tab is going to tell me whether or not we're including main or excluding the main. Well, normally excluding the main is the default that we want to use, but here this bus doesn't have a main to be excluded. The cutout or the voltage tripping device, the breaker was on a remote panel, a remote connection point, and we can see that we have extended time for calculations, and unfortunately that's kind of the next step most people take. I discourage making that leap until we really know what's going on with this particular bus. And the way to do that is to look at the coordination tripping curves of this particular device and how it relates to the bus energies. So I'm in my coordination module. I selected the bus. I don't want to do the breakers. So let's do the downstream bus and the breaker that's a problem. As we fault this bus, we see that there's the maximum current is fairly substantial at 14,000 amps. If I'm displaying a single bus fault current at half cycle, I can right-click on the TC curve and insert the arcing tick mark. And as I do that, I can see that the arcing current for this particular bus is actually about, well, it's less than half of what we're showing for the total bus current, voltage fault current. And the reason that our arcing time was so long and the energy was so high is that this curve doesn't clear, according to the manufacturer's data sheet, until well beyond 10 seconds. And while that's unrealistic, before I artificially limit the calculations for the time, what I really want to consider is what's the capability of this breaker. And as I hover over the breaker performance curve, I can see my instantaneous trip setting is at 10. If I left click, and now let's kind of look at the energy to see what's going on here. If I left click and readjust that instant energy trip, I can see by bringing that down to a 6, my tripping level now drops below 20 milliseconds, or 25, 30 milliseconds, and that gives me a respectable, or at least a comfortable, instant energy calculation. So in this case, before I start jumping to shortcuts, I think it's better to understand what's causing the problem, and my system, in this fact, does not have a design problem. It's either someone misadjusted or didn't adjust the instantaneous trip curve, or misread it when they did data collection. In any case, that would be a recommendation I would make as we complete the study. Okay, so what's the significance of whether a bus is defined or categorized as other? Well, there's kind of two answers to this question, Alex. According to the 2015 version of NFPA 70E, the specific list of devices that need labels include switchboards, panel boards, industrial control panels, meter socket enclosures, and motor control centers that are likely to require examination, adjustment services, or maintenance while they're energized. So how does it matter whether this equipment type is categorized? Well, it turns out part of the the arc flash study is a short circuit study, in which case we're trying to determine the worst case fault current at every bus and its effects on interrupting devices and whether or not the equipment will withstand these maximum potential surges. And this applies to all the buses, not just the devices that are going to be labeled. So in the case of EasyPower, the categorization of the bus will actually impact the calculations for 1584, because 1584 results will vary based on the air gap, the bus type, or the voltage. In EasyPower, bus type is affected by both, or vice versa. There's a relationship between the bus type assignment, the voltage range that it's in, and then the air gap that results. So let's kind of jump into that one. And again, both of these are areas where I think we're sorely wanting in terms of accuracy and details. So I'm looking for my bus rating example. Now, just pick out an example here for bus 5. If I come in and short this particular bus, what I want to do is compare what's going on with this particular bus and my arc flash. I can see that this particular bus is rated as other. The air gap is 32 millimeters. The arcing current and trip time are these values. Let's go ahead and take a snapshot of that and see what happens when I change my categorization. Now, the tool that I use, that I recommend using in any of these situations, actually it's extremely valuable in terms of troubleshooting errors, is the device called Database Browser. And what we're going to pick out is a single device. I could pick out subsections, or I could look at the whole list. If we pick out a single device, and this is actually more illuminating if I pick out a group of devices, go to my database browser, which is under File, Database Browser. This will show me a list of all the devices I have selected or in the system. And if I show the buses, if we're looking at bus 5, I can see I have virtually no information entered here, and certainly no rating in terms of the arc flash capabilities, and the arc flash type is rated as other. The advantage of using the database browser for this is I can double click on this particular element and the tool will bring it up for me to work on in a focus manner. And now, because I know this to be a panel, and I'm trying to verify that it's going to make a difference if it's a panel, and if I enter my bracing, let's say, is at 5,000 amps, which is probably inadequate for this purpose, but to illustrate the point, now I've got entry for my bracing, I've got entry for my arc type. As I go back to my one-line diagram and short circuit, pick out this particular bus again, and look at the arc flash results, I can see now what I'm comparing this against is, let's kind of scrunch this down, still 480 volts, doesn't matter where the trip device is, but now I've got this rated as a panel. The air gap now is 25 millimeters. The voltage fault current is still the same. The arcing current is greater. The reason for that is that this smaller air gap, when the arc forms, has a lower voltage drop across the arc, so there's more available current for the fault, which means that now my tripping device time will be less, and whether or not that changes it does change my arc flash boundary slightly, and in this case we're rounding to the first significant digit, so it hasn't changed my incident energy. The point being is that it does make a difference in arc flash calculations. Now, if I go back to the fact that I put in a rating, a bus rating, that is being incorporated in my equipment duty calculations, and now I can see that I have a fault here, and when I look at my equipment duty report, now that bus is flagged as a violation, and it would not have been had it been originally in with no entry. So the point is, without these rating devices, these rating volt current entries, we are not adequately completing the short circuit study, and consequently we're really not validating that the system's going to meet the worst case scenario. And to that point, let me kind of go through the panel. If I look at the panel and fault it and go through the same process, I can see that it was rated as a panel. It is using the correct air gap, and when I go into my equipment duty, in fact, if I go back to my database browser, I can see that by default I've set up for this panel that it is categorized as a panel, and it has a rating of 42,000 amps, which is set up as a default in my equipment palette. So these can be controlled on a global basis if I'm setting up panels, and I need to be mindful of that when I'm using discrete buses that are rated as others. Hopefully that made some sense. Okay, it looks like we're only going to make it halfway through this list, so let me kind of make this the last one for now, and we'll have to pick this up at a later date. Frequently, and as we saw in one of the examples I've used already, frequently people use incorrect utility data. Besides the transformer, the utility data is probably one of the most important parameters to accurately represent. And there is, as we use the default icon in EasyPower, the data is filled in, but it's utilizing what's referred to as infinite utility source for the first pass. Some tools on the market actually require that for their compute engines to work properly. EasyPower utilizes current injection to calculate system impedances, so it doesn't necessarily need infinite utility source, but it does need accurate data, and the data is having accurate utility data is an important first step in doing arc flash risk assessment. Another thing to look at is frequently utility companies are either reluctant to provide information or may not know anything but a specific value, and frequently it's useful to bracket a worst case plus and minus as far as what happens to our system if for some reason the utility information is off by some percentage point, and it's frequently makes sense to set up a scenario that looks at plus or minus 15% of the value that they give us. So I've made it halfway through my list. I think what I'm going to do is kind of jump to the conclusion and then pick up the balance of the list as we look at this down the road. So, and this is kind of a preview of what else is going to be coming on. So far in summary, we've looked at trying to start too fast. I think haste is the real culprit here. And by not starting with a more reasonable one-line diagram to examine exactly what's taken place, and I advocate that I sit down with my data collection team and explain why the elements that we need for data in the study are important, because it will impact the accuracy and ultimately the safety factor that we're doing the study for if people are going to be working on the equipment. And that can be imparted or understood better as people see how the calculations and the methodology should work. Likewise, if I haven't entered the data properly, I can end up with kind of a mess that's difficult to wade out of, and I recommend having a go-to protective device that works in every situation, and the best place to put it is the most central voltage source, which in most cases is a utility. And we'll pick this up later on in the list, but I think we need to be very careful when we're automatically limiting time in any part of the calculations, but specifically in 208 volt parts of the system. More and more as we see data centers in the industry and buildings requiring arc flash study, we will be seeing circuitry that has significant current available in the 208 volt system, and I think it's important that we properly characterize how the protective devices are going to work, and rather than just automatically limiting the time for calculations, we make sensible recommendations based upon sound engineering assessments of the circuitry. The classification of a bus makes a difference, both in the short circuit results in equipment duty and in the arc flash calculations, because of the variations that the IEEE model assigns as we go through the calculations. And then finally, the infinite data source doesn't really exist, and we should be mindful of how frequently our systems will be less safe the softer the utility supply is, and that's reflected in a more realistic value of arcing current. Appreciate your attendance this week. Again, next week we're starting a 4-part series, Arc Flash Made Easy, so we'll pick up the balance of this list at the end of that, and so you can register to attend that 4-part series on EasyPower.com. By all means, if you have an opportunity to check out the new feature on the EasyPower website, Knowledge Base, I invite you to visit that frequently. I appreciate everyone attending today, and I apologize for cutting it short, but the list grew as I was putting the material together. So we'll have the second half of this presentation in about 5 weeks. By all means, anyone wanting to try the tools out online at the EasyPower.com, there are demo versions that can be downloaded, and you're welcome to contact us. My email is jim@easypower.com if you have any specific questions. Have a good day.